Good morning, everybody. Welcome to the Master Thesis Defense of Javier Marin. He's going to present his work on temporal network embedding using classical multidimensional scaling. Javi, you have 30 minutes, and then we will ask you some questions. So the floor is yours.
Okay, thank you very much. I don't know if there is some noise in the background. I don't know if it's from the grabar la
Yeah,
meeting.
maybe we mute the microphone so you can start. Yeah.
Okay. Thank you. Well, as Miguel said, thank you very much. I'm going to present my master thesis. I'm going to defend it. My two tutors has been Lucas da Casa and Luis Arola. The contents for this presentation, we are going to review a little of the theoretical concepts in temporal networks, then some concepts from time series analysis and dynamical systems we need to understand better the methodology and the results. But then, of course, we are going to see the algorithm of classical multidimensional scaling, and we will briefly review some related work on network embedding. Then we will talk about the methodology, and then we will see the results obtained in the work. Then we are going to discuss them in the conclusions. But we are going to see the main references, and then I will ask all of your questions. Well, this introduction is going to be very brief, since, well, here in complex systems, we all know about networks. We know that many real-world data sets can be modeled as networks, since nodes usually represent entities, persons, or maybe particles, and links represent interactions. We can represent a network with n nodes, with an adjacency matrix, and with no loss of information. And we know that each element of the adjacency matrix is one if there is an edge between the node I and j in the element ij, and is zero otherwise. But we jump into temporal networks, which is the main thing in this work, since, well, we have that temporal networks are just sequences of snapshots. What is a snapshot? A snapshot is an static network, the networks we all know from network theory. Well, we have a sequence, an ordered time sequence of them. Each snapshot, we will say, that has n nodes, and of course it will be described as an n-square adjacency matrix. But why do we need temporal networks? Because, well, someone can argue, why use temporal networks when we already have networks? Somehow it seems like a little tricky. But the short answer is because of the time scale separation between structure and dynamics in the network is shared. And what is the dynamics of a network? Is how the network evolves over time, including changes in all links, connection, all this kind of stuff, information spreading. We all know about epidemic spreading, right? And the structure refers to the particular arrangement of nodes and edges, and how they are connected. Depending on this time scale separation, we have three types of networks. The first ones are the ones we already know, the static networks, in which the statics, the changes occur much faster than the structure. That's why we keep the structure the same. We study the network the same. We compute all these things, number of triangles, clustering coefficient, shortest path length, and all this stuff, because the nodes are kept the same. The nodes are the links. And in the other hand, we have the ensemble networks, in which the structure changes so much we have to consider the average of all the different configurations we can measure. Then the case of the study here, when the structure, how the nodes are connected, and the things going on in the network happen to occur in the same time scale. This is the perfect timescale for temporal networks. And in other words, it means that not all the links are active all the time. There is a more subtle thing to characterize from temporal networks, and it's burstiness. If we look at real-world data sets, we will see that the inter-event time distributions, well, we have described a temporal network as a sequence of snapshots, ordered sequence of snapshots. Each snapshot is happening at T1, T2, so on until Tn. If we describe the inter-event time distribution of empirical data, we will see a fat-tailed distribution. We all know some famous fat-tailed distribution, such as the power law, right? And this is bursty. And I'm going to put an example that you will understand very clearly. In the other hand, we have a random or Poisson process, like the disintegration of a particle in physics, which is not non-bursty. This tells us that this inter-event time distribution tells us that links are not activated at random. There are correlations in the generation of the links. There is a structure behind the generation of the links. A very simple example of this is if we think of a school of some classrooms with their teachers and their students, the lecture that are given during the lectures. The interaction between the teacher and the students is very high, usually, right? Then maybe in the lunch break, when all the kids are in the schoolyard, maybe the different grades interact with each other in a different way, and they interact less with the teacher. When they come back, maybe they come back to the more or less same dynamics as before. And then when they go home, the interaction disappear. Here, the interaction are, for example, talking between two people, right? So what I'm trying to say here is that links do not appear by magic. They appear because they somehow answer some structure behind the temporal network, behind the system. Maybe the sociology, maybe it's biology, maybe it's whatever the complex system represents. So just for the sake of clarity, why temporal networks? Because maybe not all the links are active all the time in the system we are modeling, and maybe links are not activated randomly. They follow a certain structure. They have a certain pattern. We will see some concepts very briefly because this is formulas. They are very important to understand and assess the results we're going to see later, but they are just formulas and tools to use. The autocorrelation function measures the correlation between observation of a time series separated by lag we are going to call tau. This helps us identify trends, periodicity, and somehow some dependencies in the data. The formulas is shown here, and well, you can see a very simple example of an ACF of a white noise time series, in which we can see that for lag tau equal to 0, the autocorrelation is 1, then it drops immediately and it fluctuates around 0 for increasing lag. Now, the natural evolution of the concept of autocorrelation function for a time series is done in a temporal network, in a series of networks. So now we can compute the autocorrelation matrix with that formula, and taking the trace of the autocorrelation matrix, we have the scalar network autocorrelation. That is the thing that we are going to compare in the results to see if the thing that we are going to call network trajectory later, or scalar projection, somehow follows this scalar network correlation that will be the ground truth that we want to see. Now, the next tool is a dynamical system tools and the Lyapunov exponent. We all know that this number, this tool, this magnitude quantifies how quickly nervy trajectories in some chaotic system diverge over time. Positive lambda means mean chaos. Okay, this is the formula when the n equal to tends to infinity. That means that the time series is very long, and f prime is just the derivative of the function, the right hand side of a map equation. And then, well, we have the here a very basic example in which we take two time series generated with the logistic map, which is the equation shown there with parameter r equal to 4 and slightly different initial conditions. And we will see that the log differences between the series show exponential diverge. And this confirms the chaotic dynamics. And this is reproduced later. Now, very briefly, we are not going back to the first year in the degree in physics. We are not going to linear algebra no more, but spectral composition of a matrix here is important. We all know that we can express a matrix as a sum of its eigenvalues and eigenvectors. This formula contemplates all of them, but the decomposition is key in some dimensional reduction techniques like PCA or multidimensional scaling, the one used here, because the matrix can be truncated by just taking the most important eigenvalues and eigenvectors. What are the most important eigenvalues and eigenvectors? Usually the largest ones. Okay, 1, 2, 3 eigenvectors, and we can truncate and somehow make a series expansion. The physicists, we all know this, right? Now, the multidimensional scaling algorithm. Well, this is just an algorithm, but the important thing is that multidimensional scaling visualize the similarity between objects. Here, the objects are going to be the snapshots of our temporal network, and they will be represented as distances in a lower dimensional space. The input is going to be a distance matrix computed with some distance we need to define, okay? The algorithm applied to n objects consists in squaring the distance matrix, centering the matrix, then taking the m largest eigenvalues and eigenvectors, and constructing with those eigenvectors and eigenvalues the output matrix that is very important because the row I of X are the new coordinates in the lower dimensional space of the object I. So we somehow have can reduce the dimensionality of something very high dimensional and obtain a lot of information, right? Some related work, network embedding, very quick. You know that we've reviewed node embedding, classical node embedding. This is not discussed here. Now we discussed temporal embedding, and of course it's done in various forms in literature, but here and in the article of Masuda et al., the approach involves embedding the entire network snapshot at each time into a single point or vector in a low dimensional space. This will give us a discrete time series. We aim to capture both a structural aerodynamic and dynamical aspect of the evolving networks with the distance between 2 points on the trajectory. And this project shares many things in common with Masuda et al., but we focus on different generative temporal network models with prescribed dynamics, and we assess the accuracy through autocorrection functions and Lyapunov exponents using classical multidimensional scaling. In that article, Masuda et al. Explore time decay networks and used landmark multidimensional scaling. We will see the methodology. Maybe this is the most important thing here in my master thesis. It's about the tool. It's not about the more or less the result or that. It's about the simulations and how we do them. The goal is to develop a method that produces low dimensional time series from a temporal network while preserving the relative position of each snapshot. Why? Because we want to apply dynamical system and time series analysis tools to that network trajectory. And this is a graphical element I implemented to explain this. We have a a temporal network, a sequence of snapshots here. Each snapshot is one, and its adjacency matrix, A1 or AET in the teeth snapshot. Then with those adjacency matrices, we can compute the distance matrix, and the distance matrix we use this distance measure, and with that output, the output is the low dimensional network trajectory. In this case, I put it 1D low dimensional network trajectory, and each point of the trajectory, for example, this one, the first one, correspond to the first snapshot. So we have transformed a snapshot, which is an element of an n-square space, into in this particular case into a 1D point. Okay, so this is correspond to suppose that these 7 points, red points that are shown here, are like 7 snapshots in the top, right? And we want that the distance between 2 points, for example, this first one and this third one, the distance between these 2 points on the trajectory indicates the difference between those snapshots at 2 different times in the reduction. So we are pretty ambitious because an n-square dimensional space is very big, but the intuition is that the adjacency matrices are going to be very sparse, so they are not to contain they are not going to contain plenty of information, right? And we aim to validate this result to know that we are confident using this in another systems. The first validation is pretty straightforward, since we just extracted a time series from the 0-1 interval uniformly at random. We construct the distance matrix using the Euclidean distance shown here. We then extract just one component of the on the matrix X we've told before in the classical multidimensional scaling. And of course, we have a 1D time series. The reduction should reflect that a 1-1 relation, and this 1-1 relation appears here. This bijection appears here. The scalar network trajectory and original values obtained from the 1-0 interval are shown to be equal. The same result is obtained in a 2D time series in which X and Y are generated separately from the 0-1 interval, but the coordinate X is generated in one way and the Y coordinate is generated in the same way, and we obtain a bijection in both coordinates. This is very straightforward because this is the result we should obtain, actually. Now, the most interesting part, synthetic temporal networks. First, we are going to generate periodic temporal networks with this formula. Gij is the adjacency matrix element ij of the teeth snapshot of the temporal network. As you can see, every element in the adjacency matrix is going to have this sinusoidal part, cosine with period equal to 10. And then we'll have a random Gaussian noise added. The aim is to check whether the time series shows a period, the network trajectory, which is a time series, shows predicted behavior with the same period we have generated, right? And using the distance we've seen before, we obtain that the temporal, the time series, the network trajectory follows. There are some points that are a little bit naughty, but they follow the trend and they have the period equal to 10. The gray dots here, they do not appear here, for example, but because they're just the trajectories of all the individual elements in the adjacency matrix, because it's the noise which is different for every element in the matrix. So this is a decent result. The network trajectory captures this predicted behavior considering the amount of truncated information we've taken. Then with the dictionary tree, we are going to build a dictionary of temporal networks that are chaotic. Very briefly, the dictionary trick, we will set the number of snapshots we want. Then we will have an initial network U1, which is an error range network with parameter P, which is just the probability of forming edges, you know. Then we will, the subsequent following networks, G2 from GL, they are going to be formed seeing the previous network and rewiring edges and ensuring that no network is repeated in the process. Then we will associate to this sequence of networks a time series that is between 0 and 1. The first value, the smallest value, the closest to 0 in the time series is mapped to G1, and the closest to 1 is mapped to GL. And this construction allows the temporal network to inherit the properties, the dynamics of the time series. Now, what is the simulation, the result we have obtained? How was the simulation done? Well, we have a time series that's generated using the fully chaotic logistic map, which is the logistic map with a parameter r equal to 4. Then, with the dictionary tree, we generate a temporal network. We generate another time series with a slightly different initial condition, with a very small change, a very subtle change. And then with that, we have a second temporal network. We mix them, we mesh them, and we project into 1D that whole temporal network. And one thing we have to do about the parameters is that we have to ensure that the number of networks chosen remains bounded by the expected number of edges in an error range network, because this will prevent redundancy in the temporal network dictionary. And now we have all the network trajectory, but that network trajectory comes somehow from two dictionaries. So we uncouple the network trajectory into set K and set prime K. Set K is the scalar projection of the first dictionary, and set prime K is the projection of the second dictionary, generated from a different initial condition. The plot is in logarithm scale. It's the same as the one shown before. And we can see that the red line and the first 13 blue dots have a slope very close to the theoretical slope. So the network trajectory actually inherits the chaotic dynamics from the chaotic logistic map. Then the DARP model, the last one of the synthetic models view here. This is a discrete autoregressive network model, and in which each link evolves independently by replicating its state from one of its past P state. That's why P is called memory order, or it updates randomly. This means that this system has prescribed memory. Well, the simulation goes as always. With the DARP, we generate somehow not a dictionary of networks, a sequence of snapshots. We're referring with that, and then we compute the network scalar ACF, and it's compared to the scalar ACF of the network trajectory. Okay. And what is the interesting thing about the DARP? I think this is one of the most interesting results in my project, in fact, because we have that the DARP model exhibit two key behaviors, and this is shown very clearly here. For tau, for lag, lower or equal than the memory order P, for example, here 8, we can see that the correlation remains constant, okay? There is a flat line there. Then the correlation decays exponential, because it's in logarithm scale, which is the y-axis, is a straight line. This means something. As you can see, the first one with the scalar projection is done with P1 is not very good, but in all of them, the scalar projection, the network trajectory, captures the constant correlation of the DARP, and then somehow with a different slope, but it has the same behavior of the DARP model. This is interesting. In these simulations, 10 nodes were used. This means the adjacency matrices needs 100 entries. So we have taken 100 entries and all that information and compressed it to one number. And that one number, that just one number has the prescribed dynamics of the DARP. I think this is huge, if you ask me, okay? And now we are going to review the empirical temporal networks. And this is just a data set my tutor Lucas and other researchers in the IFISC has worked, and it is just about politicians in a Democratic National Committee of 2016. And well, each node is one person, and the edges are emails, and they are directed, okay? And well, the dataset has its senders, recipients, and timestamps. And timestamps should be normalized to define a temporal resolution that captures the dynamics of the temporal network. We have very big sparse adjacency matrices because, well, we're going to comment that, but there is a period of low activity. And then classical multidimensional scaling, as always, is used to project the network trajectory to 1D. Okay, and we compare the network ACF with the scalar ACF, and as you can see here, well, it is obviously it is real world, but it is not a bad result because the peaks of the scalar ACF coincides with the peaks with the of the network ACF. And this is good. And in fact, it is periodic per week. As you can see, the first day, well, there is a peak. After 7 days, there is a peak. After another 7 days, there is a peak. And after another 7 days, there is a peak. So there's something going on. And considering that we have just take one number, one dimension in the reduction, this is huge already. And in fact, another point of view in here, this is what is represented here is the first component of the multidimensional scaling, of the output of dimensional scaling. So that is the network trajectory itself. You are seeing the unknowable, right? The network trajectory, the thing that has been a little obscure. We have computed ACF and all this kind of stuff. And in the paper correlations of network trajectories from Lucas, we have seen that in this particular data set, there was a period of low activity till day 466. And this is captured, as you can see here, by the network trajectory with just one dimension. But it appears like a non-stationary somehow noise, right? Because this in here, it was very stationary. But then, as you can see, it becomes more noisy, and this is the period with higher activity described in there. We're going to review the conclusions, okay, the results. Well, this project has developed the methodology we wanted. We used CMDS for dimensionality reduction of the temporal networks into a thing called network trajectory, which is just a low dimensional time series that describes, that inherits the temporal network dynamics. The method was validated in simple and complex synthetic networks, and it captures key dynamics like periodicity, chaos, and memory. And well, it is applied to an empirical dataset too. In all cases, the ACF or the network trajectory with the network ACF and Lyapunov exponent, it follows what we expected, right? The validation is okay. While effective, we can still do some things. The first thing that comes to my mind is use more dimensions. We are just using one, so we use more. And we can also study the method robustness to different distances because we only have used one. And well, this project just is a foundation for a future project that takes the time series network trajectory and uses link prediction and time series for a casting. And well, this is offering a new way to understand complex systems, okay? Just the main differences were this, La Casa correlations of network trajectories, Masuda embedding trajectories, and of course the paper of Annalisa, which is a PhD candidate, Lyapunov exponents for temporal networks. And the two ones I wanted to to use for this presentation, which are from for temporal networks. Just wanted to thank Yurai and anyone who has seen the presentation for the attention. I would like to thank both my tutors, Lucas and Luis, and I will not want to leave without thanking my family, my mother Lina, my father Francisco, my sister Lina, my grandparents, my cats, my dogs. I love them all, especially my dog Dino. I miss him every single day. And my friends, this is for you all. Time for the question. Thank you very much.
Thank you, Javier. Probably now the recording can be stopped. I don't
Okay.
know if Lucas is still there or...